In this video, we will explore in detail the working principles of a wind turbine. Wind turbines convert the kinetic energy of wind into electrical energy. Now, we will analyze a 2 megawatt wind turbine as our example. The number of homes this turbine can power varies by region, depending on average electricity consumption. In terms of physical dimensions, this generator is massive. Its tower is 90 meters high, and the rotor diameter is 90 meters. The total height from blade tip to ground reaches 135 meters. To give you a better sense of this scale, 135 meters is about the height of 35 average houses stacked up, or equivalent to a 40-story skyscraper. The rotation speed of the blades varies between 10 and 19 revolutions per minute, RPM, depending on wind conditions. When reaching rated power output, the speed typically stabilizes at 14 to 17 RPM. So, how exactly does the wind drive these massive blades to rotate? The operating principle of wind turbine blades is very similar to an airplane wing. They are designed to generate lift when wind blows across them. The blades use an airfoil design. This carefully engineered cross-sectional profile maximizes the conversion of wind energy. When wind hits the blade's cross-section, air flows faster over the curved upper surface of the blade and slower along the flatter lower surface. According to Bernoulli's principle, this creates a low-pressure area on the upper surface and a high-pressure area on the lower surface. This pressure difference generates an upward force known as lift. Lift pushes the blade toward the low-pressure area. The direction of lift is perpendicular to the wind direction and acts as the primary force driving the blade rotation. Drag, on the other hand, opposes the blade's motion. It is caused by friction generated by air molecules interacting with the blade surface, as well as pressure differences across the blade surface. Next, let's learn some technical terminology for the blades to better understand their shape and function. The blade root refers to the part closest to the hub. It connects the blade to the rotor hub and transfers all loads, including bending, torque, and gyroscopic forces, to the main shaft. The blade tip is the furthest end of the blade, where the movement speed is fastest. The airfoil is the cross-sectional shape of the blade, designed to maximize lift generation. The leading edge is the front edge that contacts the wind first. The trailing edge is the rear edge where airflow leaves the blade surface. The chord is the straight line distance connecting the leading and trailing edges. The pitch angle is the angle of the blade relative to the plane of rotation. This angle is adjustable to control power output. Wind turbine blades are thicker at the root and wider, gradually tapering and narrowing towards the tip. The blade structure acts like a large cantilever beam. Internal bending stress is highest at the fixed root, gradually decreasing along the length of the blade, and is zero at the free tip. To withstand this maximum bending, the blade root requires the largest and strongest cross-sectional design. This tapered design also serves an important aerodynamic function. The blade root moves the slowest, while the tip moves the fastest. For a rotor with a 90-meter diameter spinning at 15 RPM, the speed at the blade tip can reach approximately 210 to 250 km/h. The wide, thick root, moving at slower speeds, is designed to generate high starting torque to help the rotor start spinning in low wind speeds. Conversely, the narrower tip is designed to minimize aerodynamic drag during high-speed movement. Because the blade tip moves through the air faster than the section near the hub, and wind hits different parts of the blade at different angles, the blade typically has a 10 to 20 degree twist from root to tip. This ensures the pitch angle along the entire length of the blade remains optimal. This twisted design improves power generation efficiency and prevents blade stall. To generate the 50 Hz AC electricity required by the grid, the generator speed must be controlled within a limited range. For a typical 4-pole generator, the speed needs to be maintained at around 1,400 to 1,600 RPM. However, wind speed is always changing, so a pitch mechanism is used to rotate the blades around their longitudinal axis, regulating how much wind energy the blades capture to maintain the optimal rotor speed. The blade root features an integrated bearing mechanism equipped with an internal ring gear. The outer ring of the bearing is bolted to the hub, while the inner ring is bolted to the blade. This bearing design allows the blade to rotate around its own axis while ensuring a solid mechanical connection between the blade and the hub. The pitch mechanism uses a synchronous pitch motor installed inside the hub. Its rated speed is approximately 1,500 RPM. However, the torque of this motor alone is insufficient to overcome the wind force and rotate the massive blades. Therefore, a multi-stage planetary gear system is needed to increase torque and reduce speed. In this generator model, a two-stage planetary gear system is used, with reduction ratios of 5 and 6 respectively, giving a total reduction ratio of about 30. Subsequently, a large internal ring gear is driven by a pinion gear, resulting in a final transmission ratio of about 350. The pitch motors operate automatically based on wind conditions. Each blade can be controlled independently to achieve optimal performance and load balance. Wind turbine blades are not completely rigid. They possess a certain degree of flexibility. In high wind conditions, aerodynamic thrust pushes the blades backward, causing them to bend towards the tower. If the rotor were perfectly level, strong gusts could cause the blade tip, when rotating to its lowest point, to bend enough to strike the tower. To avoid this, the rotor shaft is tilted upwards, making the blades rotate in a plane angled away from the tower. This design increases the distance between the blade tip and the tower wall, known as tower clearance, ensuring safety even if the blades bend under maximum load. For a standard 2 megawatt wind turbine, this tilt angle is typically between 4 to 6 degrees. The bed plate is the key structural component enabling rotor tilt. You can think of it as the chassis of the nacelle, or a rigid base frame. Although the tower is completely vertical, the bedplate acts as a structural wedge. The bedplate is usually a heavy cast iron or welded steel structure. It is not a flat plate, but specially geometrically designed to achieve the tilt effect. The bottom of the bedplate is a flat horizontal surface, while the top surface where the main shaft and gearbox are mounted is machined to an incline. When the main bearing and gearbox are bolted to the bedplate, they automatically tilt slightly upwards, eliminating the need for complex bent shaft designs. The components themselves are straight, only the platform they are mounted on is tilted. The hub shape is not a simple structure, but a complex hollow 3D structure. It has 3 large precise angled openings for installing blade bearings, one opening at the front and a large opening at the rear to connect to the main shaft. The hub's internal structure features ribs and webs that can withstand immense structural loads while leaving enough space for the pitch system. The hub transfers the mechanical energy from the rotating blades to the main shaft, typically made of cast iron or ductile cast iron. For a 2 megawatt generator, it weighs about 17 to 18 tons. The hub must withstand various forces from the blades, including torque, bending moments, and gyroscopic forces caused by wind changes. Inside the hub sits a hub control unit responsible for controlling the blade pitch mechanism. It connects via slip rings to power the pitch motors. The center of the rotor is a flat metal block. Wind hitting this flat surface would create drag. Therefore, an aerodynamic cover or spinner is installed at the front of the rotor hub. Although the spinner looks like a simple cover, it plays several critical roles for the generator. Usually made of lightweight fiberglass, it is resistant to corrosion and harsh weather. Its curved shape guides airflow smoothly outward towards the blades, improving the overall efficiency of the turbine. At the same time, it shields against rain, snow, salt mist, and lightning strikes, protecting the expensive pitch system components inside from environmental damage. The main shaft's role is to transmit the low-speed rotational force from the hub to the gearbox. The main shaft is mechanically bolted to the hub and supported by 2 main bearings. These 2 bearings ensure the main shaft remains aligned and stable during rotation, while absorbing radial forces, axial forces, and tilting moments. This protects the gearbox and other downstream components from excessive stress. The main shaft uses a hollow design. This design ensures a high strength-to-weight ratio while reducing material usage. The hollow interior also serves as a passage for electrical wiring and data cables required for pitch motor control, enabling electrical and data connection between the nacelle and the hub. The main shaft connects to the gearbox input shaft via a shrink disc coupling. The gearbox input shaft is hollow and the main shaft is inserted into it. The shrink disc coupling is a high-strength, keyless mechanical connection used to secure the hollow shaft onto the solid shaft. The shrink disc is installed on the outside of the hollow shaft hub. It tightly squeezes the hollow hub, causing it to firmly grip the internal solid shaft. During operation, the 2 act essentially as a single unit. A standard shrink disc typically consists of three parts. First, a ring with a tapered outer surface, the inner ring. Second, two rings with tapered inner bores, the outer rings, whose taper angle matches the inner ring. Third, high-strength bolts used to pull the outer rings together. When the bolts pull the two tapered outer rings towards each other, the outer rings slide along the tapered slope of the inner ring. The reduction in spatial volume forces the inner ring to shrink inward, exerting immense radial pressure on the hollow shaft hub. This pressure caused the diameter of the hollow shaft to shrink slightly, tightly clamping the solid shaft and forming a friction fit around the entire circumference. The generator needs to reach a speed of about 1,500 RPM to generate 50 Hz AC electricity. However, the wind turbine rotor speed is only 14 to 17 RPM. Therefore, a gearbox with a total ratio of about 100 is needed to step up the speed to the required level. This generator model uses a three-stage gearbox consisting of one planetary gear stage and two parallel shaft helical gear stages. Planetary gear systems are preferred for the high torque input stage because the load is distributed across multiple planet gears, usually 3. In this model, the planetary gear stage ratio is 6, and the parallel helical gear stage ratios are 5 and 3.3 respectively. Through the entire gearbox transmission, the final speed is about 100 times the input speed. In this gearbox design, there is a hollow shaft extending from the input end to the other side of the gearbox. This hollow shaft rotates with the input shaft and does not contact other gear shafts. Cables from the main shaft's hollow passage pass through this gearbox hollow shaft, providing a path for wires to reach the other side of the gearbox. A slip ring assembly is directly connected to the hollow shaft extending from the gearbox. This device is used to transmit power and data signals between rotating and stationary parts. The slip ring rotates with the shaft, while stationary carbon brushes slide on the ring, maintaining continuous electrical contact. Wires connected to the carbon brushes connect to the nacelle control unit via the slip ring system. Power for the pitch motors and data signals from hub sensors are transmitted bidirectionally with the nacelle control unit through this system. A composite disc coupling is installed between the gearbox output shaft and the generator input shaft. This coupling connects the gearbox to the generator. It not only transmits rotational power, but also accommodates various misalignments between the two shafts. The composite disc pack has flexibility to absorb misalignment deviations while possessing sufficient torsional stiffness to efficiently transmit torque. More importantly, this coupling provides electrical isolation between the gearbox and the generator. The non-conductive composite material prevents harmful currents from leaking into gearbox bearings and gear teeth, avoiding premature wear or damage to these components. This wind turbine uses a doubly fed induction generator, DFIG, to generate electricity. This is a variable speed generator capable of producing electrical energy at constant voltage and frequency, even under varying rotational speed conditions. In the structure of a doubly fed induction generator, the stator is directly connected to the grid, while the rotor is connected to the grid through a back-to-back power electronic converter. The rotor windings connect to the power converter via slip rings equipped with carbon brushes. The converter can inject power into or extract power from the rotor at precise slip frequencies depending on operating conditions. This system allows the generator to operate over a wide speed range, typically plus or minus 30% of synchronous speed, while still outputting stable 50 Hz frequency power. The operating modes of a doubly fed induction generator mainly include the following 3. Subsynchronous operation. When the generator speed is below synchronous speed, the power converter injects power into the rotor through slip rings and brushes. This extra rotor excitation enables the generator to produce grid-compliant power even at lower rotation speeds. Synchronous operation. When the speed reaches 1,500 RPM, synchronous speed, the rotor requires minimal excitation current, and almost all power is generated through the stator. Supersynchronous operation. When generator speed exceeds synchronous speed, excess power is induced in the rotor windings. This excess power flows through the slip rings and brushes to the converter, which then feeds it back into the grid. Since only about 25% to 30% of total power is transmitted through the converter, the doubly fed induction generator system is more cost-effective and efficient than a full converter system. There are 3 main technical terms describing wind turbine speed limits. Cut-in, wind speed. The lowest wind speed at which blades start rotating and the generator starts producing usable power, typically 3 to 4 meters per second. Rated wind speed, the speed at which the generator reaches its rated max output, 2 meters, typically 11 to 16 meters per second. Cutout wind speed, the maximum wind speed for safe operation. Exceeding this speed, the generator will automatically shut down to prevent damage, typically 21 to 25 meters per second. Next, we will analyze the operation of the pitch control system across different wind speed ranges. Below cut-in speed, less than 3 to 4 mmPa, wind is insufficient to generate power. Blades adjust to an angle of about 90 degrees, known as fully feathered. The leading edge faces directly into the wind. This state minimizes aerodynamic lift, avoiding unnecessary rotation and preventing component wear. From cut-in to rated wind speed, pitch angle is held at approximately 0 degrees. This is the most efficient state for energy capture, maximizing lift generation to extract the maximum available energy from the wind. From rated to cutout, wind speed. The pitch angle is actively adjusted, typically between 0 and 30 degrees. This is the pitch system's most active phase. The control system gradually increases the pitch angle to shed excess wind energy, keeping the generator at its rated 2 megawatt output and preventing overload of the generator and drivetrain. Above cutout speed, greater than 25 mph, blades fully feathered to 90 degrees, aerodynamically stopping the rotor rotation. Once rotor speed drops sufficiently, a mechanical brake activates as a secondary safety measure. The hydraulic brake system is located on the high-speed shaft between the gearbox and the generator. During normal operation, the brake is disengaged. Hydraulic pressure from a hydraulic power unit holds the brake calipers open. When wind speed reaches the cutout limit, blades first slowly feather to 90 degrees to stop the rotor aerodynamically. Only when rotor speed is sufficiently low is the mechanical disc brake engaged to lock the rotor in a stationary position. The brake is used for emergency stops, such as pitch system failure, grid disconnection, overheating, or during maintenance work. The brake system uses a fail-safe design. By default, springs provide braking force and hydraulic pressure is required to release the brake. All components of a wind turbine must operate continuously for 20 to 25 years. Therefore, effective cooling systems are vital. The gearbox and generator are the primary heat generating components inside the nacelle. Gearbox cooling usually involves an oil-to-air heat exchanger, radiator mounted on top or at the rear of the nacelle. Fans draw air from inside the nacelle, push it through the radiator, and exhaust it outside. This design removes heat from the gearbox oil while preventing hot air from re-entering the nacelle. Generator cooling uses an air-to-air heat exchanger. The system contains two separate sealed air circuits. An internal circuit uses a blower to circulate air in a closed loop through the generator interior. This air absorbs heat from generator windings and components, then flows through one side of the heat exchanger to cool down. The cooled air then recirculates back into the generator. An external circuit uses another set of blowers to continuously draw air from the nacelle, pass it through the other side of the heat exchanger, and exhaust it outside. This design transfers heat outside while preventing dust, moisture, salt, and external contaminants from entering the generator interior. This closed-loop design ensures efficient heat dissipation while protecting the generator from environmental pollutants. Wind direction is constantly changing. Therefore, a wind vane or anemometer is installed on the nacelle roof to monitor wind direction in real time. The yaw system rotates the nacelle to always face the wind directly, maximizing wind energy capture. A large diameter yaw bearing is installed between the tower top and the nacelle base. The yaw bearing's inner ring is bolted to the nacelle base, while the outer ring is bolted to the tower and features an external ring gear. The yaw system is driven by multiple yaw motors, typically 4. These motors are similar to pitch motors but require a larger reduction ratio to generate enough torque to rotate the nacelle against wind forces. In this generator model, each yaw motor is equipped with a multi-stage planetary gear system. The 3 planetary gear stages have reduction ratios of 5, 6, and 6, totaling a ratio of 180. Finally, a pinion gear meshes with the yaw ring gear, providing an additional 15x reduction. Therefore, the total reduction ratio of the yaw system is approximately 2,700. Sometimes, due to continuously shifting winds, the nacelle must rotate continuously to stay facing the wind. After rotating 2 full turns, the cables running from the nacelle to the tower base may become twisted. When this happens, the generator will stop and the yaw system will rotate the nacelle back to the initial position to untwist the cables. The yaw brake system prevents unwanted nacelle rotation. Its default state is braked, provided by spring force. Multiple sets of brake calipers are bolted to the nacelle, pressing brake pads against the tower flange. The system is equipped with an independent hydraulic power unit to provide pressurized fluid. During yaw adjustment, the hydraulic system applies pressure to the calipers, compressing the springs to release the brake. When adjustment is complete, hydraulic pressure is released and the springs automatically reset to reapply braking force, locking the nacelle in position. The tower design must support the massive weight of the nacelle and rotor, while withstanding powerful wind loads, bending moments, and vibrations. Similar to the blades, the tower is tapered. Since bending moments increase from top to bottom, the tower diameter is largest at the base and gradually decreases upwards. The tower is a hollow tubular steel structure composed of multiple sections. For a 90-meter tower, it is usually divided into 3 to 4 sections. Sections connect via large flanges secured with bolts. The weight of a 2-megawatt wind turbine tower is typically between 190 to 255 tons, depending on height and design. Inside, there are ladders and a service lift for technicians to access the nacelle. Platforms are provided at section connection points, serving as rest areas and allowing inspection of flange bolts. To prevent corrosion, the steel surface is coated with multiple layers of durable paint, resisting corrosion, rain, UV radiation, and environmental wear, ensuring a 20-25 year lifespan. Power cables, control cables, and data cables from the nacelle run down through the hollow tower to the tower base. A main control unit is located at the base, usually in a separate ground-mounted cabinet or control room. This unit monitors and controls the entire turbine operation, including pitch control, yaw control, braking, and grid connection. The generator produces electricity at 690 volts. This voltage is too low for efficient long-distance transmission. Therefore, a step-up transformer is installed at the tower base to step up the voltage from 690 V to 33 kV. The transformer is typically pad-mounted near the tower base for easy access and maintenance. To support the tower, a massive foundation is required. The foundation anchors the turbine and safely transfers all loads, including the weight of the tower, nacelle, and rotor, as well as wind pressure and strong lateral forces and overturning moments from rotation, into the ground, ensuring stability and structural integrity. This type is called a gravity foundation, a large, shallow reinforced concrete structure relying on its immense weight to hold the turbine down and prevent the tall tower from tipping over. A typical gravity foundation for a 2-meter turbine is about 15-20 meters in diameter and 2-3 meters deep. Inside the foundation is a precisely engineered rebar cage. This complex steel reinforcement assembly, placed in the center before concrete pouring, contains large anchor bolts connecting the foundation to the tower base. Because wind turbines are tall and exposed in open environments, especially in lightning-prone areas, the risk of lightning strikes is high. A single strike can cause catastrophic damage to blades, electronics, and other components. Therefore, the following lightning protection measures are taken. Each blade tip has an independent air terminal receptor designed to provide a preferred attachment point for lightning. These terminals connect to down conductors, thick cables embedded inside each blade. These cables run through the blade interior, hub, main shaft, and tower, finally connecting to the grounding system. An additional lightning rod is installed on the nacelle roof to protect internal components. All down conductors connect to a comprehensive grounding system at the tower base. This system is a critical safety network designed to provide a safe path for dangerous currents from lightning or electrical faults to flow into the earth. The grounding electrode for a 2-megawatt turbine is integrated directly into the concrete foundation. This is known as a foundation earth electrode. Its primary electrode is the interconnected rebar network embedded in the concrete. Through specialized clamping and welding, the entire rebar cage forms a massive conductor. Its huge surface area and close contact with concrete and soil make it a highly efficient electrode for dissipating electrical energy. The foundation rebar also connects to a ring electrode, a continuous copper or copper-clad steel conductor installed around the foundation perimeter, typically buried 0.5 to 1 meter deep. The ring electrode connects to multiple vertical ground rods, usually 2 to 4 meters long, driven deep into the ground to reach more conductive soil layers, improving system effectiveness. This comprehensive system ensures currents from lightning and faults dissipate safely into the earth, protecting personnel, equipment, and structures. These remarkable machines, embodying decades of engineering innovation, provide sustainable power to thousands of homes while operating reliably for 20 to 25 years in harsh environmental conditions. This concludes the detailed explanation of wind turbine structure and principles. Thank you for watching, and see you in the next video.